Okay. I think no, I guess we are starting 13.2 today. We didn't do anything in 13.2 last time, did we?
No, we finished 13.1
Yeah,
last time.
that's where we ended. Okay, well then, I think you've heard everything, all the news. Uh, there were some people in my first class this morning that hadn't been there on Monday, so I had to tell them, make sure everybody understood. I am going to start doing a couple things differently. Um, I started off posting things on announcements, and then I found the message bar, and I thought that was just an icon for the announcement. So I thought it was easier to do because on my end it looks you're doing almost the same thing. So I just thought that's what I was doing. Well, I found out later that things that I was doing on announcements, people were still looking for them on announcements, and of course they weren't coming when I did the message. So I started doing both ways. And then I found out this morning that an iPad, or at least the iPad this one student had, would not show messages at all. So he had no way of accessing my messages. So I'm going to go back to only doing announcements. Everything I'm going to send is announcements. I'm going to check messages because some students are responding to my messages, but I'm just going to do everything with announcements. Is there any disadvantage of that you can think of? Is it the same?
No.
Yeah, same to you? You see the announcements, you see the messages too, right?
Yeah, I see all that.
All that, okay. Obviously, not everybody does, so I'm just going to go with announcements for my part, but then I'll be checking both, there's no way that people respond to announcements unless they do it through a message or through an email. And he's doing everything, the one that I was talking with this morning is doing everything through email, so, because he can't even access that. Okay.
Did you see that Dawson is here?
Say this again.
Did you see that
Oh,
Dawson
no, I
is
didn't.
here?
Okay, welcome, Dawson. Dawson, can you hear me yet? Okay, so there's two of you listed now, right?
Yes.
Okay. I think I've got so many things open that it just doesn't show, but this morning it showed two people plus myself. Now I only see you, but I don't see you. I just see your name. So I don't know why it changes as the day goes on, but anyway. So we are recording. Okay, a couple of things. I doubt if any of you will access this or do anything, but they do have just about everything that we were doing when we were on campus. They are providing online. If you need to contact the business office, there is actually an email, business office, and that's written as one word, no spaces, no underlines, nothing, just business office at lawsonstate.edu. Records, it's not records office, it's just records with an S at lawsonstate.edu. So everything is going to go virtual like that. The tutoring is, there was a message this morning, so check your emails. It went to all students about how to access the Space Center, the Counseling Center. Everything is trying to do things. Advisement is going to be online. Now, both of you are getting ready to graduate, I think, so you probably won't take much more advising. But, it's just, it seems like just about every office is coming along pretty quickly. I see Dawson now. I don't see you, but I see your name. Can you hear me yet? All right, good. So it seems like just about every feature that we had on campus is now virtual. And if it's not, they're moving that in that direction. So, of course, I don't know how in the world they're going to do the bookstore, but that's another issue. They probably are going to be find ways to do that as well. So, any questions about anything? Now, let me just make sure. I know Dawson said he was going to take differential equations this summer. Patrick, were you planning to take any courses this summer?
No, I wasn't.
Okay. I knew that. I think I asked that of Thomas, and I think he said that too, that he wasn't going to take any. I thought I heard Jonas say he was graduating this term, so I took that to mean he wasn't going to take any either. But anyway, the spring schedule is being redone to reflect the fact that we're going to be virtual. Okay, there will be a few online classes, as there always are, but all the other classes are being offered just like this. I mean, maybe not Zoom or Screencast-O-Matic or something, but they're being offered virtually so that we actually meet at a certain time. Everybody gets to be there at that time. I just also record them so anyone who can't be here can catch up on it. So if you do want to do anything this summer, even if you're going to be elsewhere and you did want to take a course, everything we're offering is going to be a few online, most of them virtual, just like this is. So just wanted to let you know that. Spread the word around, because Lawson is still open for business. It's just that we're not open on campus for business. But we're going to be doing just about everything we normally do, just do it remotely. So, any questions? All right. Where we left off last time was in Chapter 13, which is functions of several variables. We finally finished 13.1. 13.2 is limits and continuity. Okay? That's what we're moving to now, if there are no questions. The objectives here: understand the definition of a neighborhood in the plane. Okay? And by the way, we had an enormous, probably at least 120-year-old oak tree that after some of those heavy rains we had a few weeks ago, it just decided to lay down and quit. And it did. It just fell over. And it tore up some of our driveway, and there are plenty of other roots under our driveway, and the guys came to work on the driveway today. Is any of the noise in the background bothering you?
I haven't noticed any noise in the background.
Okay. You probably thought it was my stomach. No, I'm sorry. We won't go there. Okay. So if it does get too loud or anything, let me know. I can move to the next bedroom over that's a little bit further from where they're working there. It's just a window. And, we're sitting back from that, but we're on the back side of the house. They're more in the front, but we're on the same side as them. So here's our objectives. Understand the definition of the neighborhood in the plane. Not Mr. Rogers's, but anyway. Understand and use the definition of the limit of a function of two variables. Oh, we're going back to this, huh? Extend the concept of continuity to a function of two variables, and extend the concept of continuity to a function of three variables. So let's start out with our neighborhoods. Okay. Before we get going, well, neighborhoods in the plane. So guess what? We're starting in the plane. Okay. Using the formula for the distance between 2 points, x and y, xy and x0, y0. Those are our 2 points. xy is 1 point, x0, y point, x0, y0 is the second point. And both points are in a plane. Of course, if you have 2 points, you're in a line and you're also in a plane. You can define the delta neighborhood. Now, it's no surprise they use the term delta if you think back to our earlier formal definition of a limit. That's that same delta. Okay, delta neighborhood about that second point, the x0, y0, to be a disk centered at the x0, y0. You see the picture right there, with a radius delta always being delta always being greater than 0. That's going to be your radius, delta, always greater than 0. Radius of 0 makes no sense. That would be a single point. That would be x0, y0. You couldn't have a second point, xy. So radius greater than 0. So here's your standard old definition of the distance. The set of all xy points, no, I'm sorry, this is the definition of a neighborhood based on the distance formula. I was going to say that doesn't make a lot of sense here. Okay, so the neighborhood would be the set of all xy points, xy, such that the square root of x minus x0 squared plus y minus y0 squared is less than that delta. So in other words, what's that saying to you is you're everywhere in the pink here, okay? Everywhere in the pink. Because it's strictly less than here, I'm going to get my pen color back if I can. Well, the computer is not doing very much. Here we go. All right. Because this is strictly less than, you can't include the boundary. So that's why the boundary is dotted. So, but the delta is anything less, the point xy is anywhere less than that delta. Delta would be right on that boundary, so anything less than that. That would be what they call an open disk. Closed disk would include the boundary, but this is an open disk. So this is what we mean by neighborhood around the point x0, y0. Pick a delta, any delta greater than 0, pick a delta, and you define a neighborhood around that point. Okay? Pretty simple concept, right? And you use the distance formula to describe it. When that formula contains the less than equality sign with no equal sign in it, just less than, strictly less than, the disk is called open. And when it contains less than or equal to that symbol, then you're a closed disk, okay? And that corresponds to the use of less than and less than or equal to define open and closed intervals. If you think about that in let's see how to say it. When you're doing functions of one independent variable, putting it that way, then you would talk about the interval along, say, your independent variable. And you would either do less than or equal to, A is less than or equal to X is less than or equal to B. That would be a closed interval, and you would have brackets there. Or less than, A was less than X is less than B. That would be an open interval. You'd have parentheses. So what were your brackets are now the solid circumference, and what your open bracket or your parentheses were before, those are the dotted circumference now. So that's how they're making the connection. So let's now imagine a region R. Okay, there's a region R to be a set of points in the plane. Again, we're dealing with neighborhoods in a plane. Set of points in a plane. A point x0, y0 is in R. A point x0, y0 in R is an interior point of R if there exists some delta neighborhood around that point, all the way around that point, such that that whole neighborhood is also in R. Okay? Now, that's what we call an interior point. If you can draw the entire circle, now remember delta can be as small as you want to, it just has to be positive, it can't be 0 or negative, but as small as you want to. So even if you're really close to the edge, but not on the edge, you can just make a really tiny little delta, and you'll be an interior point. But if you're on that boundary, okay, then you're a boundary point. You cannot draw an entire neighborhood around that point that would be inside. You just can't do it because you're on the boundary. No matter how small you make the delta, as long as it's greater than 0, part of that neighborhood is going to be out of bounds, literally. Okay, so that's what we mean the difference between an interior point and a boundary point. Reflect back to Calculus 1 when we were talking about absolute maximum and minimum. Remember, if you included the endpoints, that would be on the boundaries, then you could have an absolute maximum or minimum. You always did. But if you did not include that and you only include the interior points, then that's the same type of deal we're talking about here. Okay? So a boundary point is something that's on the boundary. An interior point is anything inside that boundary. Okay. Now it sounds like, why are we wasting all this time with that? Well, the words are important. If every point in R is an interior point, then R is an open region. Okay? If every point in R is an interior point, then R is an open region. Well, now that almost sounds like, to me, it's going in circles. Certainly. Well, let's think. What if this region here had a hole in it? I'm not talking about a neighborhood, a hole in it. Well, then every point in R would not be an interior point, because this point right here would be inside the R, but it's in a hole. So that wouldn't be, and it's not even on the boundary. It would be, mine looks like it's awfully close. So that's what they mean, an open region, if every point in R is also an interior point. Now the point x0, y0 is a boundary point of R if every open disk centered at x0, y0 contains points both inside R and outside R. Okay? Okay, I'm sorry. I introduced that other thing a bit too soon. What they're saying here, let me go back. This is an open region because every point in that region is an interior point, right? Because the boundary is not included. This is a closed region, not with my point in the middle. I thought that's what they were talking about here. That's not what they're talking about. This is closed because the boundary is solid, okay? So that's a closed region. Sorry. Yeah. If R contains the interior points and the boundary, then that's a closed region. Okay. Now that is just some definitions. There is an article at the bottom, and by the way, I thought they were going to mention her. Sonia Kovaleski is mentioned on the left-hand side margin of your page. And it says that it attributes much of the terminology used to define limits, continuities, and other with this in function of 2 or 3 variables introduced by the German mathematician Karl Weierstrass. Okay? His rigorous approach to limits and other topics in calculus gained him the reputation as the father of modern analysis. He was a gifted teacher, and one of his best-known students was this Russian mathematician named Sonia Kovaleski, who applied many of Weierstrass' techniques to the problems in mathematical physics, became one of the first women to gain acceptance as a research mathematician. Brilliant, brilliant woman, but as all the women of her age and genre experienced lots and lots of resistance. They did not want women to be even considered in positions such as that, and yet her mind was so great they couldn't resist. Okay, so there's 2 possible paper topics right there: Weierstrass or Sonia Kovaleski. Well, now, why would I mention something like that? Oh, maybe because I don't have a paper from anyone in this class, and we're in our last month that you can submit a paper. This is April Fool's, right? No, this is April 1st. We are now in the last month. Please don't fail to get your paper in. Remember how you can submit it? Either attach it as an email or attach it to a message, if you can do a message. And I was telling Patrick earlier, Dawson, that I found out this morning in my first class that at least one student's iPad would not let them receive or send a message through Blackboard. And I don't know why. One of my other students said it's the app. I know what an app is, but I don't know what he means is the app. It's the app's fault. I don't know who comes up with the app. Was that Blackboard? Was it? I have no idea. But we looked at it. He held it up to the screen. No one could figure out how to get to a message. So he couldn't receive any of my messages I was sending, and he couldn't send any. So if you have that kind of limitation, please send it as an attachment to an email. If you don't, you can choose either one. Okay. If you send it as a Word file, I can open it as a Word file and do it that way. If you, for some reason, want to just send it as a PDF, you can scan it. I can receive those. If you want to just send it as a picture taken by a smartphone, so far I've been able to receive all those that students have sent. So get me the file any way you can, in any format you can, and then either by email or through the message app on our message icon on Blackboard. This new Blackboard is just coming up with more and more limitations that I can't explain. But anyway, that's that. So let's move on to page 885, and this is limit of a function in two variables. And don't worry, this is not going to be quite as painful as our first rendition of limit, which took an entire chapter. This will basically be this section, and we'll move right along. So the definition of a limit and a function of two variables: let f be a function of two variables defined except possibly at that center point, x0, y0. It may be defined there, but it may not be defined there. But except for that point, it's defined everywhere on the open disk that contains that point, x0, y0. Then let L be a real number. That, by the way, is going to be the limit. Then the limit as xy, the point xy, the variable point xy, is approaching that fixed point x0, y0 of the function f of xy. The limit of that would be L. That's how you define a limit. Okay. Now here's the sounds just like the formal definition. That's true if for each epsilon greater than 0, there exists a corresponding delta greater than 0. There was that delta again, greater than 0, such that if the absolute value of f of x minus L, think of this as since it can't be the y value anymore, we'll call this the z value. The difference between this and the limit, the difference between the absolute value of the difference, is less than that epsilon anytime you guarantee the point xy as approaching x0, y0, just like we said before, that distance formula, if that distance between those 2 points is less than delta. So if you can guarantee that you can get the difference between f of x, the actual function value, and the limit to be less than the smallest epsilon you choose to do, as long as epsilon is greater than 0, choose it as small as you'd like. If you can find the delta that makes that happen, then that limit does exist, no matter how small you get. Okay? It looks just about like it did before. This part looks exactly the same. This part here used to just say, basically, x minus x0 is between 0 and delta. Now you do the distance of the 2 points, because you got two variables now. Okay. Graphically, the definition of a limit of a function of two variables implies that for any point x, y not equal to x0, y0, so here at the center of your disk is your x0, y0, and the function may or may not be defined there. This, it looks like it is. Okay, and then inside that delta, inside that disk, okay, delta disk, that's pretty convenient too, you have an x1, y1, or just an xy. I don't know why they put ones here, no ones up there, but anyway, any point inside there, that this picture is not all that helpful in my mind. What we have here, and frankly to me this looks like this picture is more confusing than it's worth. What this green cylinder is here is the extension of this disk upward, or that's at least what it appears to me. So these two points are inside that cylinder, okay, on this plane. Here is your function, that plane that goes down there, that's the function. So somewhere inside the cylinder on that function, there's the center of it. It may or may not be defined there. That's your x0, y0. Here is your x1, y1, or what they were calling up here, xy. That's also inside the cylinder because it's inside that disk down here, and that's down somewhere here. Well, the difference between the limit, which is the actual, you think of the value at that point there, the x0, y0, even if that doesn't, if not defined, if there's no value there, but that's the limit as it's going to, is within the epsilons, which are between here, and again, they haven't drawn this very well in my mind. You can choose an epsilon, and you guarantee that this point is going to be between L plus epsilon and L minus epsilon. Okay? Now, as long as this point down here is inside your delta. Okay. So if you pick a tiny, tiny, tiny little epsilon here, then you just shrink your delta until you guarantee that the point is inside that. And yeah, as long as you can find a delta small enough to fit that, then the limit exists. If there's some value there that beyond that you can't guarantee that anymore, the limit doesn't exist. Okay? So that's basically all it was saying. This part looks the same as before. Before we just had, you were on the x-axis, but it's pretty much where the y-axis was. You could expand or well, usually contract your delta, which would be the distance between the x0 and here. Before it was one-dimensional, now it's two-dimensional. So it's within a disk. Okay. A lot of blah, blah, blah about something that you probably won't wind up using that much. But anyway, the definition of the limit of a function of two variables, except Patrick. Patrick is probably going to be doing this for his whole life in mathematics. Okay. The definition of the limit of a function of two variables is similar to the definition of the limit of a function of a single variable. When they say that, they mean two independent variables, and this is a single independent, single independent variable. Okay, I like to put that in there because in reality this is a three-variable case. That's a two-variable case. Yet there is a critical difference. They're similar but not quite the same. Here's the difference. To determine whether a function of a single variable has a limit, all you need to do is you need only test the approach from two directions, from the left or from the right. And remember, we did that. The limit had to exist from both directions. Okay? However, if you are in three-dimensional, like we're here now, when the function approaches the same limit from the right, this is talking about single independent variable. From the right and left, you conclude the limit exists. What we're dealing with now, for a function of two variables, the statement xy approaching x0, y0 means that the point xy is allowed to approach x0, y0 from any direction it wants to. And even though maybe from every direction in the world except one or two, the limit does exist, if there is a direction where it doesn't, the limit doesn't exist. So if the value, the limit as xy approaches x0, y0, f of xy is not the same for all possible approaches or paths, that's how we're going to call it, to x0, y0, then the limit does not exist. even though for the vast majority or almost exclusively, if there's still one or two paths for which it doesn't exist, the limit doesn't exist. All right. Now this is one that almost drives you crazy because it's so simple. Okay? So the limit as xy approaches AB of x is going to be a. Well, guess what? If x is approaching a, the limit is going to be a. I mean, that's what I mean by this is such an incredibly simple problem. It'll drive you crazy figuring out if you're really proving it or not, because it seems to be just obvious in its statement. Okay? So rather than fight with it, let's just show exactly how they approach it. Let your f of x, y be x. Yeah, that's what goes in here. F of x, y. In this case, it's just x. The limit is what goes out here. That's your a. Why they have two different a's, I'm not sure, but they do. One's an italicized regular script A, and the other's italicized fancy A. You know, they are the same a's. Okay. What you need to show here that for any epsilon greater than 0, any epsilon you choose, no matter how tiny, there exists a delta neighborhood around this point AB such that the absolute value of f of xy minus L, this minus that, which is, by the way, x minus a, there exists a delta neighborhood about that such that the difference there, whenever xy is not equal to AB, lies in that neighborhood. Okay? Now, this is what makes it so incredibly simple. I mean, almost too simple to think about. The definition of xy is x. F of xy is x. The limit here is a. And when you write it this way, guess what you just have? There it is. You basically have what you wind up with here. If y minus y is 0, if that's not changing, that disappears. And then you have x minus a. Square root of x minus a squared is x minus a. So your epsilon's the same as your delta. And that's what, to me, makes this one so incredibly bizarre to try to deal with. When you write it this way, basically, this is your answer. You let that equal your delta, okay? And that's all you really have to do. But they go through it in more detail. You can first observe that from 0 is less than square root of x minus a squared plus y minus b squared less than delta. It follows that the difference of these two is that. We've already said that. That is exactly, this is your x, this is your a, okay? Now, that's the same as, the absolute value of x minus a is the same as the square root of x minus a squared, okay? Because guess what? This thing's always positive. This thing is always positive. I'm going to get rid of mine. Okay? Because this is the absolute value, and this is the principal square root. They're always positive, and they mean the same thing. Because if you remove the radical and this, then basically you get x minus a, but you have to put it in absolute value bars because it's positive. It's got to be positive. And a could be greater than x. So put it in absolute value, you've got it. So that's exactly the same thing. All right? Now that's less than or equal to this thing. Because we have no idea what y is, but y minus b squared is a positive quantity. And if you're adding that to this one, that means whatever is over here is less than or equal to this, because you've just added something to it. Now it's equal to if this thing you added was 0, but this over here is less than that because you just added something to this line up here, and you added a positive value. Okay? And that is indeed your delta. So that's why I was saying the whole problem is set up almost as if it answers itself. It really doesn't, but you have to work through it. It really feels like it. So you can choose delta equal epsilon. The limit is verified. Okay? Because you knew this was less than or equal to epsilon, less than epsilon, and this is also less than delta. So any epsilon you choose the same delta. You guarantee it. Okay? So limits of functions of several variables have the same properties regarding sums, differences, products, and quotients as do the limits of functions of single variables. I believe, no, that's right, okay. I was thinking they had skipped an example, but this is right before the next example, okay?
Dr. Fowler?
Yes. Oh, Fred is here.
Yeah, I just wanted to check in, making sure you was here. Also, are you recording this? Like, will this be on, are you doing screencast?
Yeah, you see the thing in the corner down here? Yeah. That's the screencast-o-matic. So all my things are recorded, so if you missed any, they're out there now. Now, let me also warn you of this. This is my second of 4 classes today, and as soon as I get out of that 4th class, I've got a virtual meeting with the dean and the associate dean, and the dean indicated that's going to be at least an hour, so I won't be able to upload anything within that time frame. I get out of class today around 6:30. So about the earliest I'll be meeting with them is around 6:30. So that's probably going to go at least until 7:30 and maybe later. And then by the time I eat a little supper and get back to it, I don't know when I'm going to get around to uploading this. So it may not be today. I'm going to try to do it before I go to bed tonight to upload this to Screencast-O-Matic. But everything before this is uploaded already. So, but yeah, I can't say it's going to be today you'll get it out there, but I'm going to try my best to get it out there today. Is that what you're asking?
Yeah.
Okay. All right. Has anyone else joined the class? I've got 3 now, Fred, Dawson, and Patrick. Still haven't seen Ryan since the first day we did a screencast. And Josh was here the last 2. Say again?
I think Ryan is sick right now.
Oh, is he?
I know he said that. Did we have class on Monday?
Yes, we did.
Okay.
Now here's something I did, and I didn't realize that it was making a difference. And I apologize if it cost you something. But, and by the way, we're going to have class just about every Monday and Wednesday. Just like if we were in school, I'd try never to miss a class. Now that I'm home, it's going to be even better. I have even less reason. But what I didn't realize before, I had started making the announcements on the announcements, okay, in Blackboard. And then someone, I don't remember how I found out about the message, which is the little envelope symbol. But somehow I found out about that and realized, and that everything I would do to do an announcement, I was doing the same thing on message. So I thought that was just a shortcut to the message that saved me a few clicks. So I just started using the messages because I started getting stuff in from students through messages. So I went, so I thought, well, let me just do messages then, since I have to check them every day. That's what I'll do. But I thought they were the same as the announcements. Well, I found out yesterday that they weren't. And that's why on Monday, I had just sent it through message. I didn't send it through announcements because I thought it was the same thing. And then today I found out at least one student who is using an iPad that he doesn't even get to see the messages. So he can't send a message and he can't receive a message, not if he's using an iPad. Now, therefore, from now on, everything I send from here is going to be through an announcement. But I'll be receiving things. You can't receive anything through an announcement. I thought the message thing just enabled you to do that, but it doesn't. I can receive things through a message or I can receive them through email. So if you can't see the message icon, then send it to me through an email. But if you can see that, you can use either one you want to. I'll be checking both of them. And I can't say I'll check them every day. I'm going to try to check them every day. But yesterday, I didn't even make it through all my emails before I ran out of time. Because I was losing it anytime after 9:30. I'm just become sort of a no good whatsoever. So I was just making more mistakes when I was typing. I said I'm going to call it quits. I'm going to blame it on my low red count, that I just don't have the stamina I used to, but it may be I'm just getting old. I know I'm getting old. So, but anyway, I will be checking both emails and messages, but I'll only from now on be sending things through announcements, because I realize I didn't know before today that some people don't get messages and can't get messages. So I'll be doing my end through announcements. You can do your end either through emails or messaging, either one. Do you know what I mean by message?
Yeah, I was just looking at it just now. I saw what you're talking about.
Yeah, it's that on that top bar when you're in Blackboard in the course, under the content, there's a little bar up there, and one of the bars is a grade book, or one of the icons is a grade book, one of them's a message, one of them's discussion, one of them's other things. Well, this guy, he showed me on... Was that someone talking to me?
Sorry, that was my background noise.
Oh, okay, good, okay. I was thinking, oh, this class doesn't have any females. Okay, never mind. So anyway, he showed the thing, and there were no icons in that little gray bar up there, none whatsoever. And that's when all of us in the class realized, oh, he can't receive a message, so therefore he can't send the message. So everything I've been sending by messages, he hasn't gotten. So if you were in that boat and looking under announcements, because that's where I started, I thought that's how you sent things. And then when I saw that, I thought, oh, here's the icon for announcements. It wasn't. That was just for messages. But on my end, they were identically the same.
Yeah, because that's what on Monday I was looking for the announcement for the Zoom and I didn't find it, so I didn't know if we had class or not.
Yeah. Well, I would say check them both, but I'm going to quit sending anything through messages unless I find out some people can't get announcements, then I would go back to doing both again. But I think everybody's getting the announcements, so I'm going to strictly do that way. Now, I also sent the second test through, I think, message. Did anyone not get the second test? You may have been in class that last day and gotten it then, because I passed it out.
I got a physical test.
Yeah, you got the actual paper one. Okay. If you check in messages, I sent a virtual one too, just because I could. Well, I had to do it for 3 people, I think, so I just put it out there for everybody. But I'll quit doing that. I'll just do it through announcements. Okay? That way I'll know everybody gets it. Because I didn't know people weren't getting both of them. Because I thought the two things were the same. A bad assumption on my part. All right. Now, picking up where we were, this is the top of page, wait a minute. I think we have skipped something. Yes, the wording, the paragraph at the top of page 886 was there, but then the 2 examples on 886 are not there. So let's go back and find white space. Now that's a good amount of white space. I think it's actually more white space than that one. So we will go to this white space and do example 2 and 3. finding a limit. What is the limit as your point, your variable point xy approaches your fixed point 1, 2. I can't. Now it starts doing this, it seems like worse in the afternoon. I think my system gets tired. Okay, approaches 1, 2. It just gets to the pen won't write. Okay, the limit as xy approaches 1, 2 of 5x squared y over x squared plus, the pen's just not writing, y squared. Okay. Now, I wonder when I'm writing and the pen's not, do you see the little black dot going across and no line following it? Or were you paying attention to that? That's what I see on my side. I'm writing on the screen, but nothing's showing up. I go back and write again, and then again, and about a few minutes later, all the lines will show up at the same time. I don't know why it does that, but it does. Now, how many of you want to use the formal definition? Oh, I don't see any hands going up, okay? How do you think we might choose to do this? What do you do with Glade?
We should take the x equal 1 and y equal 2.
Why not? Okay, just plug it in. See if the limit exists. Now, I'm sure they're going to want, no, actually they're doing this, okay? I think that's how they're doing it. So let's do exactly what I think it was Patrick said, okay? That will be 5 times 1 squared. See, I wrote a square and part of the 2 showed up and part didn't. Times 1 squared times 2, that's the y part, over 1 squared, that's the x part, plus 2 squared, that's the y part. What does that give us? Numerator is?
It gives us 10 over 5.
10 over 5, which is 2. Okay. Now, and I think you'll always figure it out if there's a problem like this, but the only thing you have to watch for is to make sure that you haven't overlooked the fact that you couldn't do something, and that sounds sort of stupid, but in this problem it's pretty obvious. The only thing you wouldn't have been able to do is if the denominator would have turned out 0, and that would have become patently obvious right at the top. So that limit is indeed 2. So that was so much fun. Okay. Well, I take that back that I just said. No, it's fine. I think it would have been patently obvious. Let's do example 3, and it looks like it's just as obvious, but we'll find out it's not. Okay, anyone need this left longer? That was pretty simple, right? All right, let's do example 3. Find the limit as xy is approaching 0, 0 of 5x squared y. Well, I should have just erased the 1, 2 and put a 0, 0 in, okay, if I'd have been paying attention. X squared, I can't get it to right, plus y squared. Now, anything reach out and slap you in the face on this one?
Well, we know the denominator can't be 0, so we can't.
Unless the numerator is 0. Then you have what you call an indeterminate form, or that's what we used to call it in single variable calculus. And this would fit the bill there because the numerator is 0, denominator is 0. So you could say there is a possibility that limit could exist. Okay? Now, I'm going to tell you my shortcut on this, and I can't guarantee it will always work. But I'm going to tell you what I do on these type. I look and see what, this is a strange way to put it, what degree of 0 I have in the numerator. Does anyone know what I'm talking about there? We have x is equal to 0, but it's squared, so it's 0 times 0 times 0. But in the denominator, you only have a 0 times 0 plus a 0 times 0. So I look at that as being, the numerator as being a third degree 0, and the denominator a second degree 0. Well, guess who wins? The third degree, the one in the numerator. So in my mind, that suggests to me that 0 is the limit. Okay? Now, the problem with this is, and we're not going to hit it here, but we will hit it in other places. No, let's see. Well, this one works no matter what pathway you take. That's where the paths come into play. Okay? Now, they do it formally, which is be perfectly fine. It's a little on the tedious side, which, yeah, I'll buy that. And they get, when they get around to it, as long as the delta is epsilon over 5, this will work. In other words, no matter how small you choose your epsilon, divide that choice of epsilon by 5, you'll guarantee to get a delta that works. Now, that 5 right there is the reason for that, but it's not patently obvious why that's true. And again, I say follow along what they're doing in the book, and you can do the formal definition and see why that indeed is the case. And because it is the case, that limit does exist. And it's like I suggested to you, because you have more zeros in the numerator than you do in the denominator. Now, just because you say, well, you got 4 zeros down there, no, those are added together. That's still a degree 2. In the numerator, you got degree 3. Now, I can't guarantee that technique will work every time, but it seems to work enough times that it can keep you out of most problems. Okay. Now, they then suggest to you, and I think they give the picture, and so let's go on to that picture. For some functions, it's easy to recognize that a limit doesn't exist, like this one. And this should ring bells for what you did back in Cal 1. The limit as xy approaches 0, 0 of 1 over x squared plus y squared, no doubt here, because when you plug in, what do you get? Anybody? When you plug 0, 0 for what xy, what do you get?
You get 0.
In the denominator, what's in the numerator?
1.
Does 1 over 0 ever exist?
No.
No. 0 over 0 is indeterminate. That's what we had in the last problem. That's why you had to look a little deeper. 1 over 0 is never going to work, so don't waste your time with epsilons and deltas or anything else. Just when you see that, does not exist. Okay? That doesn't exist. There is no way it would ever exist. And here's the graph of that function, and you see it's going infinitely upward, never reaching a single point, Just keeps going up. We're getting closer and closer and closer and closer to that z-axis, but never touching it. That one doesn't exist. So, again, that rule that I always used, if you have an expression that cannot possibly ever exist, then that's a do not exist. If you have something that the denominator is 0, but the numerator is also 0, that's a indeterminate. Some of those won't exist, but some of them might. The last one did. This one will never exist. Okay. So let's go to, whoa! I can't believe they're skipping example 4. That's probably the most important example we have. So let's do it here. And this is not, if my memory is right, this is the first time I've taught from this book, but I believe this is the same as before. Now, if anything I say or do here gets you totally confused, go to larsoncalculus.com and you'll see an interactive version of this type of example, and hopefully they can make it make more sense. Okay? So here's your expression. The limit as xy is approaching 0, 0, and there again my pen's not writing. Okay? xy is approaching 0, 0 of x squared minus y squared over x squared plus y squared squared, the whole thing squared. Okay? Now, this is one in Never Never Land. Okay? What I mean by that, the numerator is, even my little technique, is degree 0. The denominator is degree 0. You're squaring something that's degree 0. I'm sorry, I said it backwards. The numerator is degree 2. The denominator is degree 2. Then you're squaring it, making 4s and 4s. Nothing's clear on this. You got 0 over 0, which is indeterminate, sure, but there's no way to tell who's winning, who's losing. Now, you might be tempted to think, because you have the plus sign here, that the denominator is always going to be just a little bit more than the numerator is. Okay? But, no. You can't tell a thing. Okay? Now, they said, show that it doesn't exist, and it's not completely clear. And they start off talking about the domain of the function. Well, the domain of that function is obviously everything except 0, 0, okay? Because that denominator, the only point that that's not defined is where x equals 0, y is equal to 0, okay? Numerator is okay there, but the denominator is not. So they start off with that. It consists of all points in the xy plane except for the point 0, 0. To show that the limit as xy approaches 0, 0 does not exist, and here's where you don't have anything equivalent to this in single variable calculus. Here you start saying, well, what happens if you come in this way or that way? Okay, now, I don't draw three-dimensional well at all. In fact, it really stinks. Okay? Let's call this our x-axis, this our y-axis, and this our z-axis. And that would be your function f. Okay? Now, the origin is the only place this function is not defined. So if you had a circle around that origin, and I did not draw it that way, the pen is doing strange things. Okay? Let's see if I can get it to, my circles are bad, but they weren't that bad, usually. Okay. Now, that's an awfully big circle. Now, what if you were coming in the x-axis, approaching 0? Let's say the y is 0 and the x is approaching 0. Okay? So the y is already at 0. What is happening as x approaches 0 when y is equal to 0? Well, that still seems to be a 0, 0. Okay? 0 over 0. So it's really not all that clear. Well, if you approach coming in the y-axis, let x equals 0, y approaching 0, you're still going to get that indeterminate form. But what if we come in the diagonal here, where x equals y? Okay? When x is equal to y, that would be this diagonal, right? Coming in there, this would be a 0 in the numerator, but it would be a 2x squared in the denominator. Squared, which would be 0 over 4x to the 4th. Right? Now, suddenly you have a situation where your numerator is just a 0. Your denominator is a 0 to the 4th power. And that would indicate to me this does not exist. Now again, that's my stupid little rule, but it seems to work in most cases. Your degree of your 0 in the denominator is greater than the degree of the 0 in the numerator. Now, I know that's a strange way to phrase it, and therefore I would say this does not exist. Now that's my strange reasoning. Okay? Now, the book carries you through this, and again, a pretty terrible detail. Okay? And what I said before wasn't quite true. Yeah. I realize I misstated something now. Let's do it this way. The limit as xy approaches 0, 0, that's not really what I want to do. I don't know how they write it. Ah, that's it. Again, what I said to begin with, or I may have said the other way first. Okay. Let's let the y be 0, and you're coming in as x is approaching 0. So let's write this form that way. Let me get my stuff out of the way. That was, probably I shouldn't have even done it. I was just showing you what sometimes my thought process is, okay? Which sometimes is pretty weird, okay? Goodness gracious. Okay. That would be this. It would be x minus 0, x squared minus 0 squared over x squared plus 0 squared. Well, what would be that? My plus didn't show up, okay? This would be 1. I'm sorry. Yeah, finally it wrote. This would be 1, and the limit as x 0 approaches 0, 0 would be 1. But if you do it the other way, the limit as 0y, that's not what I wrote, okay, 0y is approaching, okay, there it is, 0, 0, then this would be 0 minus y squared over 0 minus plus y squared. Now the problem here is the square. That would be a minus 1 but then you're still squaring it, so that's still a 1. Okay? Now, what I was saying, if you came in the diagonal like that, that would be x equal y, and that's what I was saying, and let's go and write it down again. I think I may have erased it. I can't get it to write. There it goes. The limit as x is approaching, because if x is equal to y, you could write it that way, approaching 0, 0. Okay? Then if you wrote this, that would be 0, x squared minus x 0 would be 0 over 2x squared. And that's what we did before. And you squared that, and that gives you 0 over 4x to the 4th. Well, that's obviously 0. Okay? Now, just by its own. So these two approaches gave you a limit of 1. This approach gave you a limit of 0. Hang up the phone, because you can't be approaching two different values from different directions and the limit exists. Okay? So therefore, that's the reason this doesn't exist. I went straight to this one and said, that's my degree thing. This is a little bit better because both of these were approaching 1 when you came in either of the axes, but when you chose a different route, for instance, this one, x equal y, then you get a 0 as your limit. Can't happen. Can't be two different ways from two different directions. They show a figure in the book, and that's why I wish they had shown this, and this is almost an impossible figure to figure out, out what they're showing here. They're using color as best they can, but even that leaves a lot to be desired. And I can't swear to you I can make out what it is. The lighter green color, if you got your book and looking at it, the lighter green color on the axes, that actually sits on the axis. But no, it doesn't. Again, I can't make out. They're trying to be helpful with the colors, and I can't quite make out how that thing is really doing. Almost looks like it's wrapping around something. So to me, sometimes the figure helps. This one doesn't help me at all. So now I've got to pause for a moment because I just noticed my plug sometimes, okay. This old computer, the plug and the socket don't always make great contact, especially when they get hot. And this has been running all day, and my battery is very weak. I need new batteries, but the plug is bad, and it would run down even a strong battery, so I have to look out. I think that's going to keep us going. Okay, so let's move away from 4. That's basically how they did it. Approaching from two directions, you get a 1. From a third direction, you get a 0. If you can come up with any direction that gives you a limit that's other than some other direction, limit doesn't exist. Okay, so let's move on to continuity as a function of two variables. Guess what, folks? We're through with limits. Okay, not really. We'll be using limits, but we're through with only dealing with limits as limits. We'll use them, as parts of a problem before, but that's what it is. Now, they said, notice in example 2 that the limit of, this is the one that was Let's see if they do this. I don't think they do. Yes, it is. There it is. The limit as f of x y is 5x squared y over x squared plus y squared. As xy is approaching 1, 2, can be evaluated by direct substitution. That's exactly what we did, okay? And that's what the book did too. That is the limit of f of 1, 2 is equal to 2. That's what the limit was, but that's also what the value was. In such cases, the function is said to be continuous at the point 1, 2. When the limit as you're approaching 1, 2 is 2, but the value when you calculate it is 2, then you're said to be continuous there. When you're discontinuous is when the limit is one value, but the actual calculation is another value. That means you have a hole in the graph down here, and up there or below there somewhere you have a different value. Okay? I think you remember that case. If you're coming along here and coming along here, but up here you had a value there. In single variable calculus, that limit doesn't exist. Even though the limit, the limit exists, but the limit's not equal to the function value, so therefore that would not be continuous because you have a hole in the graph there, and it's discontinuous there. Well, this is saying anytime that you have a two-variable independent variable function, that the limit exists and also the value existed there, that's said to be continuous at 1, 2. The same function was not continuous at 0, 0. Because the value didn't even exist there. But its limit was at 0, but the value was not. So here's the definition of continuity of a function of two independent variables. I wish they wouldn't say just two variables. You might say, well, all our functions were x, y. Well, yeah, but y was dependent on x. So the function f of two independent variables is continuous at a point x0, y0. That's in the domain of those two variables, okay? x0, y0 in an open region, not called intervals anymore, region R, if the function f of x0, y0 is defined. There's the key. The function has to be defined at that value. Earlier we said it didn't have to be. For it to be continuous, it must be defined there. But not only must it be defined there, but it must be equal to the limit of f of xy as xy approaches x0, y0. So you don't have that case that in a region it's defined everywhere except maybe right there, and this everywhere it seems to be approaching something, and I'll just say that it's all approaching something up here. You know, it seems like everything's going there, but this value is actually down here somewhere. Okay, it's defined everywhere, but this one, the function value is not equal to the limit. The limit is up here. This is the L. There is the actual value there. Now that's an extreme example. That is, the limit as xy approaches x0, y0 of f of xy must be f of x0, y0. Now, that vertical line there, I don't know why it's there. Periodically in this, the graphics person, I don't know what happened. They just threw an extra line in there. I can't get rid of it. It's in the PowerPoint. It's just there. It means nothing. It's extraneous. The function f is continuous in the open region R if it's continuous at every point in R. So if this is your region R here, and it doesn't have to be your thing. It could be, if that's your region R, it would have to be continuous everywhere. It could not have a value like that anywhere. Okay? So that's continuous in a region R. Now, here's a function that is not continuous at 0, 0 because it's not defined at 0, 0. Because the limit at that point exists, you can remove the discontinuity by defining f at 0, 0 to be its limit there, which we determined to be 0. Such a discontinuity is called removable. And remember, we had those in single variable calculus as well. Okay, the function f of xy, that one is not continuous at 0, 0, since that discontinuity was non-removable. That discontinuity, if it's +1 from two directions and 0 from another direction, there ain't no way you're going to pick some value that would be continuous from every direction. Not going to happen. Okay, that discontinuity was non-removable. It's continuous everywhere else, but not there, not at 0, 0. And it's not even removable. So here's theorem 13.1, continuous functions of, and there's another one of those vertical lines, and I have no idea why they're there. Okay, continuous functions of two variables. If k is a real number and f of xy and g of xy are both continuous at x0, y0, then the following functions are also continuous at x0, y0. First, your scalar multiple is k times f or k times g, either one, would be continuous at 0, 0. If the functions are there, a scalar multiple of the function is continuous there. The sum or the difference of those two functions would be continuous there. Okay? The product function would be continuous there. And the quotient function would be continuous there as long as g at that point was not equal to 0. Okay? See, g could be 0 here, here, or there if that was a g. No problem. But it can't be if it's in the denominator. So as long as g of x0, y0 is not 0, then f divided by g, the quotient function, is continuous at x0, y0. This theorem establishes the continuity of polynomial and rational functions at every point in their domains. Now, that's sort of a Weasley way of doing it. Polynomial functions are going to be continuous everywhere. Everywhere. And remember, we had a expanded definition of polynomial functions. Ran into that last time. Go back and look at that. Rational functions are not continuous everywhere. But guess what? They're continuous everywhere in their domains. Well, that's what a domain is. A domain excludes the places where they're not continuous. So that is correct. A rational function is continuous at every point in its domain because the points of discontinuity are not in the domain. Furthermore, the continuity of other types of functions can be extended naturally from one to two variables. Now let's just think of a few of those. The trig functions. Sines and cosines continuous everywhere. Your other four trig functions, there are going to be some values where those discontinuities exist. You know, where for secant, for instance, it's because that secant is 1 over cosine. Anywhere a cosine would be 0, the secant function cannot exist. Okay, but that wouldn't be in the domain. Okay, because it's not defined there. Okay, so exponential functions defined everywhere. Log functions, no. Their domain, yes. All positive values. But if you can't take the log of a negative value or of 0. So if it's in their domain, yeah, it works. So for instance, the functions whose graphs are shown in this table are continuous at every point in the plane. Okay? This one is because sine is continuous everywhere. Your polynomial functions are continuous everywhere. Yeah, no problem. I'm glad they drew it. I didn't have to. Okay? Now, this one. It almost looks like there's a hole in the graph here. Okay? There's not. I don't think there is anyway. No, it can't be. It says it continues every point in the plane. Because cosine is continuous everywhere. Polynomial functions are continuous everywhere. Exponential functions are continuous everywhere. Now, square root functions are not continuous everywhere. they're not continuous where the thing under the radical is negative. But guess what? X squared plus y squared can never be negative. It could be 0, but square root of 0 is perfectly okay. E to the 0 is perfectly okay. So there's nothing wrong with 0. Any other value for x and y you put in there, whether they're positive or negative, as soon as you square them, they're positive, and you add two positive numbers together, you're going to get a positive number, or at least a non-negative number. Okay? So that will be continuous everywhere. All right. Theorem 13.2, continuity of a composite function. Now remember, composite functions in two variables were a little bizarre because if you have a g composed with h can be defined at two variables, but g is a single variable function because you see you're doing g of h here. Well, no matter what x's and y's you put in here, you can only get one output. Okay? That's what makes it a function. And because it only has one output, g only has one input. So that becomes a single variable function. So here's the continuity of a composite function. If h is continuous at x0, y0, and g is continuous at the value h at x0, y0. Now that's a single value, okay? Then the composite function given by g composed with h of xy is equal to g of h of xy. That's continuous to x0, y0. That is the limit as xy approaches x0, y0 of g of h of xy would be g of h of x0, y0. So if of course that means h is continuous at that point, g is continuous at the point where h is that value, then the composite function is continuous at that point. Note in this theorem that h is a function of two variables and g is a function of one. That's what I started off saying. Okay. Any questions? A lot of blah, 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 right? Okay. Let's discuss the continuity of these functions. That f of xy, would you say that's continuous everywhere? Or if not, where is it not continuous? Anybody? Say again?
Continuous everywhere.
Okay, except x, y equal 0, 0. The limit may exist there, but it doesn't. Not by my little rule. But it's not defined there either. You can't divide by 0. Everywhere else, it's no problem. But because that's in the denominator. Now, if that was in a, goodness gracious, the screen decided to print that, and I didn't write it. Let me see if I can get it to erase it. Okay. Okay. It's not defined at 0, 0. And like I said, there's a chance it could have had a limit there because it's an indeterminate form, but still it's not defined there. I contend there's no limit there either, but that's beside the point. All they're asking is continuity. Okay, how about B? I'm trying to say every point except that point. Wow. Okay. How about that G function? The reason this is true, x squared plus y squared cannot equal 0. That's still true. If the pen would write, it's still true, okay? And that occurs when at 0, 0. So that point is not in the domain of that function. It's not continuous there. Okay. It may have a limit there. I think not, but it's not continuous there. Now, how about B? What can you say about that? Thought I was giving you a hint.
Denominator cannot be 0.
Okay. Y minus x squared cannot equal 0. Now, can you do anything to manipulate that a little bit?
Y is equal to x squared.
Cannot equal x squared, right? Cannot equal, I'm sorry. You said it, I was doing it out in detail, but since you said it, I don't have to do this in detail. All you did was add x squared to both sides. So you say y cannot equal x squared. Now remember, our domain is in the xy axis, in the xy plane. G is in the z plane, wherever that is. Well, let's draw, that's a joke, my x, y, z, and you see I write them in and they disappear and then they don't write. I don't know what's going on here. Okay. Right. Okay. Something like that. What does this look like in the xy plane?
Parabola.
It is a parabola, opening basically something like this, isn't it? Only thing is, it can't be anywhere on that parabola. So everything except that parabola, that's your domain. In here, no sweat. Out here, no sweat. Okay, this is three-dimensional. No sweat, but it can't be on that parabola. Everywhere in the xy plane except that parabola. There's your continuity. Continuous everywhere else except on the parabola. The other one continuous everywhere except at the origin. All right, let's see how the book did it. The A part, because the rational function is continuous at every point in its domain, it is continuous at every point in its domain. The trouble is 0, 0 isn't in the domain. You can conclude that f is continuous at every point in the xy plane except 0, 0 because it's not. That's not in its domain. And you see, this makes a funnel that's going down the next to the y-axis, or z-axis, going down on one side and going up on the other side. I don't believe that 0, 0 they're ever going to meet, do you? But continuous everywhere else. Even though they're very, very far apart, there is a value, continuously value everywhere else. Okay, that's a single point. Okay, I'm glad they drew the graph. I didn't have to. Now, this one is continuous except at the points where the denominator is 0, just like the other one was. These points are given by, and they put equal to. I don't like to put equal to. I put not equal to. That reminds me they can't exist there. And that would be, they conclude that the function continues at all the points except those that lie on that parabola, y is equal to x squared. So this is sort of what that one looks like. What a weird rendition here. And what, again, it's hard drawing three-dimensional stuff on a two-dimensional thing. But you see, this is continuous everywhere outside there, except on that parabola. Down here, outside it's going to negative infinity. Inside it's going to positive infinity. Now what is hard for me to see is this parabola is coming down like this it looks like. But because the colors are the same, you can't tell that. But that's what it is. Discontinuous, big time discontinuous on that parabola. Does that make sense? Sort of.
Yes.
All right, good. Outside the parabola, y is less than x squared, so the y values will be dragging it downward, okay? And the surface lies below the xy plane. And, they didn't say that. Inside the parabola, the x squared is greater than y squared, so it's all going to be positive there above the xy plane. All right. Now that was example 5. Now let's move to continuity of a function in 3 variables, 3 independent variables. You might say, we're just doing 3 variables. No, those are 3 variables, but 2 were independent. These are 3 independent variables. The definition of the limit and continuity can be extended to function 3 variable. Consider the points x0, y0, z0 within an open sphere. Okay? Before you had an interval. Then you went to, in 2 dimensions, 2 independent dimensions, you went to a circle in the xy plane. Anything inside that circle. Okay? Well, now you do anything inside a sphere. 3 independent variables, and you happen to have one that's x0, y0, z0, and everything around that would be within the sphere. And you could have open spheres and closed spheres. It's sort of hard to draw them because it's hard to draw a dashed line around all the way around the sphere, but you can imagine that. That's an open sphere because they haven't darkened in the outside. Now the radius of that sphere is your delta. That's a sphere of x minus x0 squared plus y minus y0 squared plus z minus z0 squared is less than delta squared. I don't remember that's how they expressed it before. I think what they did before was put a square root on here and just leave that a delta. Either one of those expressions is the same thing. The radius of the sphere is delta. The sphere is centered at x0, y0, and z0 as shown here. That's now your domain, okay? Your range is something in a 4th dimension that I can't see, and I can imagine, I can't think about. I'll leave that to you. A point x0, y0, 0 in a region R in space is an interior point, and they usually don't use R for the thing in space. I thought other texts use S. They use R again. Is an interior point of R if there exists a delta sphere somewhere around that x0, y0, z0 that lies entirely in that region R in space. Now that's a 3-dimensional block. It's not a circle like it was. It's a 3-dimensional thing. If every point in R is an interior point, then R is called an open. I want to say interval. That's not what they call it. Open region, I guess. Yeah. So here's the definition of continuity of a function, 3 independent variables. A function f of 3 independent variables is continuous at a point x0, y0, z0 in an open region R if f of x0, y0, z0 is defined. It has to be defined at that point and is equal to the limit of f of x, y, z as x, y, z approaches that point, x0, y0, z0. That means that the limit as x, y, z approaches x0, y0, z0 of f of x, y, z is the point f of x0, y0, z0. Okay? This says the limit, the function has a value there. It is defined there. This says the limit of the function as it approaches that point is that point. Okay. The function is continuous in an open region R if it's continuous at every point in R. Okay. So, all they're asking here, discuss the continuity of that function. F of xyz is equal to 1 over x squared plus y squared minus z. So what could you tell me? What would be your condition here? Basically, you start it just like we did before.
Well, we know that the bottom function cannot
Right.
equal 0.
X squared plus y squared minus z cannot equal 0. Now, what does that tell you?
Z cannot equal x squared plus y squared.
Perfect. Z cannot equal, if a pen would write, x squared plus y squared. Okay? What does that mean? This is going to be terrible, but I'm going to try it. Here's your x, there's your y, there's your z. How would you define what x squared plus y squared was? Say,
It's like it's not a circle.
not quite, but it is circular in some senses. If z is 0, you'd be right there. And for c, say, is 1, then this would be a circle of radius 1, right? If z was 4, this would be a circle of radius 2, right? Is that right? Yeah, x squared plus y squared is equal to 2 squared, right? If it was 3, it would be a circle of radius 9. Okay? Same thing down here, though. Wait, let's see. Is that right?
I mean, if it was 3.
And z couldn't be negative, right? So guess what that would form?
A parabola?
Not a parabola. It comes down as a point right here. You've never done any chemistry lab, have you? All the way around, coming down. That's the top half of a cone.
Oh, okay.
A right circular cone. Okay? Now, this function would be continuous anywhere except on the surface of that right circular cone, the upper surface. Lower surface isn't even defined, I don't think, is it? Yeah, I guess you could have negative z's. Okay. So, let's see how they do it. That's a pretty sorry rendition on my part, but let's see how they do. Okay. The function is continuous everywhere except at the points where the denominator is 0, so therefore they give it as an equality. I like it as an inequality. Okay. So you're right. That was not a cone, that was a paraboloid. Sorry. Because, yeah, I'm sorry. Written that way, it's still, I was right about circular things, but it was smooth at the bottom. That's why I was having trouble recognizing what was happening down here, because paraboloids never go down there. They were circles, but it was a paraboloid, not a cone. Okay. So yeah, your answer was correct. Continuous every point in space except on that paraboloid. Inside the paraboloid, your z is greater than that x squared plus y squared x squared plus y squared. Outside of it's always less than. So that's why everywhere down below it, it's no problem at all. Okay. So that's the end of the section. Okay. Homework exercises here, and we are just out of time too, aren't we? Let me just give you quickly the homework. Always look at the concept checks. That's just for your review and reminding. Either 3 or 5, both at Calc Chat, 5's at Calc View. Wait a minute. Yeah, we're right. Okay. Either 7 or 9, both at Calc Chat. Any of the odds, 11 through 23, all at Calc Chat, 15's at Calc View. Any of the odds, 25 through 35, all at Calc Chat, 27's at Calc View. Either 37 or 39, you can explore doing those if you choose. Think about doing 39. You don't have to, that's up to you. 41 should be at Calc Chat. And by the way, those should be at Calc Chat also. 41 should be at Calc Chat. Then you can do either 43 or 45. They both should be at Calc Chat. Thankfully, they drew the figures for you. 47 should be at Calc Chat. 49 should be at Calc Chat. Any of the odds 51 through 55 should be at Calc Chat. 57 or 59 should be at Calc Chat. Any of the odds 61 through 65 should be at Calc Chat, with 61 being at Calc View. 67 or 69 should be at Calc Chat. 71 to 75 should be at Calc Chat. 77 should be at Calc Chat. And 79 or 81 are true false. They should be at Calc Chat. 83 should be at Calc Chat. 85 is a proof, and you can do that if you'd like. It should also be at Calc Chat. We'll begin next time with 13.3. Any questions? 13.2. Okay.
No, I think I'm good.
All right. Well, I hope you have a good weekend. I hope I've given you enough homework exercises to make it good. Okay. And also, I will try to get the. Now, did everyone? Okay. Did everyone get the second test? I think I asked that before. I just want to make sure.
Yeah.
All of you did.
Yep.
Okay. The only person I don't know about for certain would be Josh, because 3 of you know. I don't know about Ryan either. So those 2 were not there that Monday when I passed it out. So I'm going to have to check on that. Fred, you said you could get in touch with Josh, right? I mean, with Ryan, right?
Yeah, I talked to him on Monday. He said he just wasn't feeling well.
Right. Okay. Tell him we hope he feels better, but find out if he got the second test. If he did, fine. Okay. Otherwise, I'll put it out as an announcement rather than as a message. And Dawson, do you have any way of getting in touch with Josh?
Dawson left.
Oh, he did. Okay, sorry. Okay, any of the rest of you can get in touch with Josh. Any of you share any numbers?
No, I can't.
All right, we'll try to figure it out. Hopefully he'll show up. He was here last time, but he didn't say anything. So anyway, have a good weekend and stay healthy.
You too.
All right,
Bye.
thank you. All right, I'm ending the meeting. Bye-bye.